Alright, you guys. So I have my week 7 assignment created, and you'll see that I have put, I downloaded the field datasets. This is a file that I extracted in my downloads folder, and I went and copied the dataset for this week. It's called puppies.save, and I put it into the folder where I have my R project material, and I like to collect all this in the same spot. When you save things in RStudio, you'll notice that it saves the RMD file and the HTML file in that folder, and I put the dataset in there, and that way you have it all in one folder, and it's just easy when you're working on a project in RStudio. You're going to notice an extra file in there this week, and that is an RTF file, which stands for a rich text format file, and it's kind of a generic Word file that many different types of word processors can open. So it's not just limited to Word, but it lets you do some formatting more than just a plain text file. And I think I'm going to switch and have you guys put all your answers onto one sheet rather than save them in the body of the HTML file. I think we've done enough in RStudio with knitting those HTML files that we can probably stop doing that, but I'm still going to give you your assignment in RStudio because this is a convenient way to give them, and it keeps us practiced up on using RStudio. So now this is ready to go, and I'm actually going to change this to say put your name on your answer sheet, and we'll save that. So just so you guys can see this, I'm using Word, but this RTF file should open in just about anything, and I've put the basic steps of doing an analysis in this, and here's our chunk for data preparation steps, and now here's the bottom part with our steps for a null hypothesis significance test. And you guys have pretty much seen the whole process, and we will be following that through on the different tests that we look at this semester. So basically remember these steps, because this is kind of the steps you would take when you're doing an analysis, and put all your answers on this text file and turn that in instead of the HTML file, and I think it'll be a little easier for me to read through the answers and also help you know that you really need to answer something. So we're going to go back and look at this in case you don't have the modules installed. We left the instructions for which modules we'll use, and we're going to go through some of these steps on this week's assignment for a one-way analysis of variance. And an analysis, an ANOVA, a one-way ANOVA is pretty much for when you're comparing the means between more than two groups. You can't actually use an ANOVA to compare the means between two groups, and you'll get the same answer as you would doing a t-test, although we're using an F statistic here rather than a T statistic. And if I remember correctly, I haven't done the math on this for a while, I think an F is the same thing as a T squared, but you could run it each way and double check that. The p-value should be the same, so it doesn't make a difference if you use an ANOVA or a t-test, other than when two groups, people are used to seeing t-tests, and I would always recommend just doing the simplest test possible because more people would understand it. So we're going to use the data set out of field, and it's a puppies data set, and I'm I'm going to open up Jamovi, and then we will go open up our data set. So I'm in Jamovi. We can go into the little 3 lines that we're going to call our file menu. Go to open and browse, and I have that in the week 7 folder. We're going to open this puppies.save file. That's an SPSS data file. And I have not actually looked at this data set yet, so this is a good chance for us to look at this together. So whenever we look at a new data set, then I will give it a look over, and looking at the description in the field text in, let's see, this is chapter 12, I believe. He says this data set is looking at puppy therapy given to different groups. One group doesn't have it, one group has 15 minutes, and one group has 30 minutes. And they have a happiness rating. So I'm going to go ahead, this first check here, in looking at things, looking at our data accuracy. I didn't see any issues with weird data, but we could determine our level of measurement for each group. So so if I double click on that header, I can see this here, and that's nominal, which is groups. We could, I think, technically move that to ordinal. I think I'd call that an ordinal level of measurement, because control group doesn't get anything. One group is 15 minutes and one group is 30 minutes, so there's some order there. I'd go ahead and switch that to ordinal. The happiness rating is a continuous variable, and it looks to me like it's on a range from 1 to 7, and by my regular rule of thumb, I would actually call that ordinal because it's less than 10 categories, and it's kind of a Likert type question where it has people rate something. And this is an example where there's going to be some statistical debate over should you do things like t-tests with these ordinal types of variables, and you'll see it done all the time. There's some debate there. I've done it, and just because it's accepted and it's what we have. So technically, I would probably use a regular continuous variable here, but just be advised that this particular data I would call ordinal, but I'm going to leave it continuous for this example. And the advantage of using these data sets out of the field text is what we have, our results, match closely with the results in the textbook. And he gives some nice explanation sometimes of what's going on. I think there's some benefit to that if you're reading through it. The disadvantage is this isn't the same type of data set that we might typically look at in healthcare. However, you really can translate these tests into the universal language of statistics, and that is level of measurement. And really, I can't overstate the importance of knowing how to determine the level of measurement for a variable, because if you want to change this to different data that you understand better or that you're using for something, then you would take this nominal or ordinal variable that we have and find a nominal or ordinal variable in a data set that you want to work with, and a continuous variable that we have, and switch that for a continuous variable in your data set, and you could run this test. So and that's a skill that you really ought to pick up, because that means you'll be able to translate your statistical knowledge into other contexts. So looking at it, I didn't see anything that looks misspelled or missing. The groups make sense. The numbers make sense. But we're going to go ahead and go into analyses and exploration and get some descriptive statistics. When this is a small data set, I can look at it quickly and get a good idea what's going on. But if it's large with several hundred or thousand rows, then you're going to want to rely on your descriptive statistics in your plots to help you determine if you have any problems. So do you remember the appropriate descriptive statistics in plots for a categorical variable? And categorical is nominal or ordinal. And let's look at those first. So if you said frequencies and percents and bar charts, then you are correct. And if not, then you need to study up on that a little bit. So we really don't care. We definitely want our ends and our missing, but we don't care about means and medians, or really the spread when we're looking at groups. So we can uncheck all of those options, and I can see that I have 5 people in its group for 33.3%, and our cumulative percent goes up to 100, and we don't have any missing values. So I feel pretty good about that, and I'm going to go ahead and hit this little option and go back to exploration again and descriptives, so we can get a different section for our continuous variables. And you'll notice I start fresh. I don't have any variables in a box, so I don't have to clean anything out. And we're going to look at happiness thought this time. And this is our continuous variable. Do you remember the correct descriptive statistics and plots that we should get for our continuous variables? Pause the video and think to yourself. Okay, if you're back again, if you said means and standard deviations, that would be the correct answer. And so let's go ahead and get the standard deviation, the range. And I am interested in looking at skewness and kurtosis, since we are looking at an ANOVA, which is a test, a parametric test, and also a test based on the linear model. Then we care if we have normally distributed data or not. And let's go ahead and I'm going to look at this briefly, so we can see we have an overall mean and there's our standard deviation. When we really care about skewness and kurtosis and normality, we actually care about how it is in each group and not overall. And so you'll notice that here in my descriptives, I have the option to split this data by a grouping variable. And so that's what we're going to do. We're going to put dose in there. And now you'll see we have a much bigger chart, but it's going to split each of these things out by the individual group. And let's get a box plot for each of these and a histogram. We'll get a density curve on the histogram. So if we go here, we look at descriptives, we can see we have 5 in each group, no missing data. There's our mean for each group. And you see a couple medians are a little bit different, so that tells me they're not perfectly normally distributed. There's our standard deviations. One group's a little more spread out than the others. And If you remember, if we're looking at normality, a nice test is looking at the skewness divided by the standard error of the skewness. So 0.5 divided by 0.9, and that is going to be less than 1. And the cutoff we're really looking for there is 2. If you have a skewness divided by the standard error of the skewness that is 2 or greater, you start being concerned about your normality assumption being violated, and you may want to look at an alternative to a parametric test if you don't have a large sample size. And this sample is not 30, so it's smaller than 30. We'd be more concerned about our normality than our other assumptions with that. Kurtosis is not as big a deal when looking at normality, and so mostly I look at the skewness, but we do have a statistical test, Shapiro-Wilk. SPSS usually gives another one called the Kolmogorov-Smirnov test, or called the KS statistic, and it's a statistical test to see if these data are different than normally distributed, and it's not significant. So when it's not significant, then we determine that there's no difference between normally distributed and the data that we have. In this case, not enough difference to worry about. So we're okay there. And we've got some plots. You can see we have this density plot with our histogram. Kind of gives you that little line. These aren't, this happiness is the closest to normally distributed, but it's still kind of flat, so we'd call that platycritic. And you'll see that we have some skew on these other two groups. Box plots would let us see any outliers, and there's no dots above or below the box plots, so we're not really too concerned about outliers. So we can go back to our checklist. Everything seems to make sense. We don't really have any problems to correct here. There's no scoring of instruments that needs to be done. So we have good levels of measurement. So no missing data, no outliers. Now we're going to be looking at some statistical assumptions. So we already talked about our normality assumption, which we looked at with our histograms and also with our Shapiro-Wilks test. And we don't have any problems with normality. And remember that when you're looking at normality for t-tests and ANOVAs, that you care about the normal distribution in each group, within each group, and not overall. So you definitely want to split these out by groups when looking at that. That is something to remember. And our other assumptions for this test is this is a linear model. We care that our observations are independent, so that's one assumption, and that is something you know by study design. And we would know that these groups are different individuals assigned to different groups. These are not the same individuals with different groups. So an ANOVA is an appropriate test. That's just something you have to know from the study design. There's not really a way to look at the numbers and know if observations are independent or not. And homogeneity of variance, that's the variance between the groups. We did look at this standard deviation, and we do note that they're not all the exact same values, so we will be curious to see when we run a test on that if we violate that assumption or not. So that's something done with the Levine's test, and we will get that when we go to run our ANOVA. So we'll finish talking about that later. And before we get going, now that we've looked enough, I did want you guys to take a look at the StatCat module, and we're looking at relationships, prediction, and group comparisons, and ANOVA is definitely comparing groups. So we're going to put dose which is our categorical variable, into our independent variable. Independent is the one where you can manipulate one of the groups. So that's why dose is independent, and happiness is our dependent variable, which would normally be our continuous variable. And we can see that there's a couple different options here. There's a Spearman rank correlation coefficient, which I've never used that test before. And as we know, on these things in StatCat, you can click on these links and they will take you to a test, to a page, an HTML page that you can read about, a description of that. And we can do a one-way ANOVA. And the one they do not bring up here is a Kruskal-Wallis test, and that is the non-parametric equivalent of a one-way ANOVA that I learned when I was in statistics. So it doesn't list it here, but I do. This is still a great tool for if you're trying to figure out what kind of test you can do. So it's not perfect, doesn't list all the options, but there's something we can look at. Now we're going to go look at our ANOVA test, and if we click on the ANOVA menu in the analysis section, we can see we have a one-way ANOVA, repeated measures ANOVA. We'll talk about what these ANCOVA and MANCOVA are. We do have a non-parametric equivalent of the one-way ANOVA, which is the Kruskal-Wallis test. So if we had a violation of our assumptions, then an alternative option would be to do this one-way ANOVA. We have looked at Bayesian tests before. We're not going to worry about this with the ANOVA, but we did try it out with the t-test. And remember that the Walrus module was for robust tests in R, and we do have a robust ANOVA. So if we violate assumptions, we have a couple of different options. We can go for the non-parametric Kruskal-Wallis, which is in the past was kind of the only option. And we do have this robust assumption, and more these robust methods are what are preferred over non-parametric. But people will probably know Kruskal-Wallis better than they might know a robust ANOVA. But as we saw before, this is really pretty easy to use. Oh, and I didn't want to go there. So let's go back to our ANOVA and one-way ANOVA. And if you accidentally go somewhere you don't want to, you can just select something and remove it. And you can hear my dog Frankie moving where he's sleeping. Okay, so we're in our one-way ANOVA. I'll go fix that later. Okay, so we have our grouping variable, which we know is dose. We have our continuous variable, which is our happiness variable. And we're going to go ahead and get some descriptives. Look at our normality with those things and our equality of variances, as they call it. And I'm used to calling it homogeneity of variance, but they picked probably a little more understandable word there. And kind of the nice part of this, the way this works in Jamovi, is we can see this output while we're still running things. And so we already looked at our p-value on our Shapiro-Wilk before. We know that we didn't have an issue with overall normality, but we did a better job before because we looked at our groups separately. But here we're going to look at homogeneity of variance, which is Levine's test. And this is just like a regular mini statistical test. We still use 0.05 as our criteria for rejection. The null hypothesis is that there is no difference in the means of the groups. The alternative is there is a difference. And we see this p-value of 0.9. We know that's not significant, and we would fail to reject that null for the Levene's test and determine that there's no difference in the variances between the different groups. So whenever something gives you a p-value, it's like a mini statistical test, and you still go through those steps that we use, and we can see them on the answer sheet when we are doing our steps for an HST. We have state the null and alternative, our criteria for rejection. We calculate the test statistic, in that case it's Levene's, and we fail to reject the null on our Levene's test, so we say that the variances are equal, and we can move forward knowing that our homogeneity variance assumption is met. So Field, in his chapter, says it's never a bad idea just to use Welch's all the time on your ANOVAs, and then you're pretty safe no matter what you do. But I'm going to go ahead and check this assumption equal and get Fisher's. And it's a little bit different than it's laid out in ANOVA, but we'll go ahead and get them both. And I always use this exclude cases analysis by analysis. Here we don't have any missing data, so it doesn't matter. But if you were running several different tests, you could exclude somebody from all of the tests if they're missing data on anything that was used in there. But we're not going to do that. So now that we know that we meet our normality assumption and we meet our homogeneity variance assumption, we can check out our post-hoc tests, and you'll see there's only 2 in Jamovi. In SPSS, there's like 18 different choices, and Field gives some nice descriptions. He described a couple that I actually hadn't learned before, but Tukey is a go-to. It's kind of a nice general post-hoc test, and when you have equal variances, that's appropriate. If we had unequal variances, then this Games Howell, and I've actually never used that one before, but it's probably a good one to use when we have unequal variances. So we're going to stick with, you'll see this is a radio button, so you can only pick one option. Since we know we have equal variances, we're going to stick with Tukey. And we're going to go ahead and get statistical tests after the fact, the post-hoc tests, which let us do group comparisons. And we can just select all the options. So basically, check everything under here. And now let's go over and take a look at our results. So let's go ahead and interpret Fisher's because we do have equal variances. So we see our F statistic is 5.12, and we have our 2 degrees of freedom. And you're going to report both of those because one of those is the degrees of freedom for the model, and one of those is the degrees of freedom for the residual. And we have a p-value of 0.025, which is statistically significant. So if we were over here going through our steps for null hypothesis testing, on our answer sheet, we looked in StatCat and had a couple tests recommended. One of them was the 1wayANOVA, and you want to go ahead and fill in this answer on the answer sheet, the test that got recommended. The basic steps of null hypothesis significance testing, I give you kind of a comprehensive list, so we're not going to worry about the part where you're deciding on research questions and hypotheses, or determining your data, because that's been done for us, determining the appropriate statistical analysis. The nice part of knowing this whole process is if you want to actually run a test, you can kind of, before you even collect any data, go put that into Jamovi and see what kind of statistical test you can run on that type of data, and that might help you decide if you want to collect that or if you need to adjust what you're collecting so you can do the type of analysis that you're trying to do. And of course, we already have our data set, so that's been collected for us. So the null and alternative hypotheses for an ANOVA, our null hypothesis, or H0, is there is no difference between the means of the different groups. The alternative is there is a difference in the means of at least two of the groups. Our criteria for rejection, I talk about that in the our notebook, and we're going to stick with 0.05 for our examples, but be aware that you can sometimes choose to use 0.01 or 0.10, and I talked about a couple instances where you might do that. And here we've been able to calculate our test statistics. And you want to go ahead and give kind of a description in here of what we did. We went into the analysis section and1wayANOVA, and which options did we choose. Go ahead and list that out here, what we did. And then we're going to draw a conclusion. Do we reject or fail to reject the null? So if we go back to Jamovi and look at our p-value of 0.025, do we reject or fail to reject the null? And when that p is below our criteria for rejection, which was 0.05, then we would reject the null, and we would determine that there is a difference between at least two of the groups. Now the next logical question is, well, let's go back to our answer sheet. What is the meaning of this result when we reject the null? It's not just enough to say we reject the null. You want to make sure you understand what that really means and put it in plain language. So that means that when we reject the null for this 1wayANOVA, that there is some kind of a difference between the control and the 15-minute group or the 30-minute group, but as of yet we don't know where that difference is. And are there any follow-up analyses needed? You don't usually run an ANOVA to find out if there's a difference. You want to find out where there's a difference. So yes, there are some follow-up analyses, and those are called post-hoc tests. So we're going to go in Jamovi, and we already checked the boxes, so we should get some post-hoc tests, and there they are. So you'll see it gives us, this is the first time I've looked at post-hoc tests in Jamovi, but you'll see it puts this in a little chart. So the control group with the control group compared to the 15-minute group, the control group compared to the 30-minute group. If you go down here to the 15-minute group, we already saw the 15-minute and control group in the line above. So now we can see the 15-minute group with the 30-minute group. Those results are reported right there. And then the 30-minute group, of course, we've seen all those comparisons already. So this is not a bad way to look at it. You just have to figure out that this is a little chart. So the mean difference between the control group and the 15-minute group is -1, and this is a good place to go look at your descriptive statistics, and let's go see what the mean of the control and the mean of the 15-minute group is. And if we go up here, let's find our descriptive statistics. Control group is 2.2 and our 15-minute group is 3.2. So that means that our control group had lower happiness scores than our 15 minutes of puppy therapy group. Always take these numbers and go back to your descriptive statistics to see what those numbers mean. So our t-value is negative 1.3. I know that usually with a t statistic you want to get above about a 2 for it to start to be significant. And when I look at the p-value, 0.5, it's not significant. So that tells me there is no statistically significant difference between the control group and the 15-minute group. Let's look at the control group with the 30-minute group. Our mean difference is bigger by quite a bit, negative 2.8. That tells me that the control group is quite a bit lower than the 30 minutes of puppy therapy group for happiness scores. Our t-value is negative 3.16. That's well over 2. And not surprisingly, I have a p-value of 0.021. So there is a statistically significant difference between the control group and the 30-minute group. The last comparison is how about the difference between the 15-minute group and the 30-minute group. And I see a mean difference of negative 1.8, so there's still a good bit of difference there. A t-value of negative 2.03. We're right on the cusp, but we see a p-value of 0.147, and this is an instance where we only have 15 people in this group, so it did not achieve a statistically significant difference, but definitely underpowered. And you'll notice that I asked for significant comparisons to be flagged, and we have an asterisk next to our control and 30-minute comparison, and we have a little table down here at the bottom. 1 asterisk means it's less than p.05. 2 asterisks would be less than p.01, and 3 asterisks would be less than p.001. So that's handy to note that this is our one statistically significant difference. So when you go into let's go look at our description of the assignment here. So we followed our steps, and we did our one-way ANOVA, looked at our variables, looked at our assumptions for independence and normality and homogeneity of variance, did our null and alternative, criteria for rejection. You're going to put all that information on your answer sheet. And did we meet our statistical assumptions? We did. We calculated our one-way ANOVA. And what decision would we make about the null? We rejected the null because there was a statistically significant difference. And then we needed post-hoc tests to find out where that difference was. And Field gives some nice description in his chapter on that. I give you this section. And we're going to report the appropriate results. And Field in 12.11 gives a nice description of a short report on that. But we would report, let's bring up my answer sheet. I did give you the basic things that you could fill in here for your F, and these are going to be your degrees of freedom. I think they were like 2 and 12, but let's go back and look at our degrees of freedom on our F, and let's see here. This is one thing, don't mess this up. Our Levine's is also an F statistic. We do not want the results from Levine's test, but we do want our F from our ANOVA. And since we know our assumptions are equal, I'm going to uncheck this Welch's box, and we'll just report our Fishers because we already know that we tested our homogeneity variance assumption. So let's just make this output a little bit easier to read so we don't make mistakes. So our F statistic is 5.12, and our degrees of freedom are going to be 2 and 12. And then our p-value is going to be 0.025. I'm going to pause this for 1 second.